Okay, so we've been working toward graphing polynomial functions. That's where we're heading, and we're still another step in that process. Before we get there, we're going to deal with polynomial equations. So some of the aspects of polynomial equations will allow us or help us in that goal of graphing polynomial functions. So I keep trying to bring this up. One of the keys in graphing polynomial functions are the zeros. So one more time, if you had to graph a polynomial function, if you find that perhaps a zero is, say, -3, and maybe another zero is 0, and perhaps a third zero is 2, then we have a general idea of the way this function goes. We're also going to learn some aspects of whether this thing starts from positive infinity or starts from negative infinity, and whether it ends heading toward positive infinity or negative infinity. So again, if we knew it started from negative infinity and ends in positive infinity, we'd find some other points, but we'd end up with a graph that looks something like that. So again, the zeros are the key. In solving a polynomial equation, you only have one variable, right? Let's go back and think of the chart, whether something's an equation or a function. Equation, one variable. Function, two variables, x and y. So with an equation, we're only going to have one variable. And so we're going to solve these polynomial equations. When you solve for a zero, you set the y variable to 0. Giving you, in effect, an equation with only one variable, the x. So solving a polynomial equation is synonymous or similar to finding the zeros of a polynomial function. Okay, so that's the tie-in, and that's the relationship there. And again, we'll get there here real soon. Tomorrow we'll start with polynomial functions, but we've got to deal with equations today. And so the start of it all is with the fundamental theorem of algebra. And it infers that there are as many complex number roots as the degree of the polynomial. As many complex number roots as the degree of the polynomial. All right, so we got a polynomial there, x cubed minus 2x squared plus 5x minus 6. And hopefully we all determine that this thing is a third degree. What a way to start a Monday morning, giving you the third degree. All right, awesome. It's a third degree. And so according to the fundamental theorem of algebra, there are going to be three roots. Three complex number roots. By the way, complex again involves real and or imaginary numbers, so both real and imaginary. Okay, so how about the number of zeros? So in the second example, we have a function, because we have a y and we have an x, two variables. So we got a function. We can all see it's fifth degree. So this one is a fifth degree. And here's the reality. With zeros, there's not a definite 5 of them. There's up to 5 of them. So we'll say less than or equal to 5 zeros. Less than or equal to 5 zeros. Up to 5 zeros with a fifth degree polynomial. 10th degree polynomial, up to 10 zeros. 40th degree polynomial, up to 40 zeros. Third degree, up to 3 zeros. Okay. And then the third thing we can conclude is also in the area of solutions. In the area of solutions. So, and this really shouldn't be a function. This should be a 0 here and an equation. So in this situation, hopefully you look at this and you say this is a fourth degree. And I should have said this earlier. Remember, the degree of a polynomial is the degree of the highest degree term. The last term is fourth degree. That's the highest degree. So this polynomial is fourth degree. And so here again, there are greater than or equal to 4 solutions. The only reason I say, I said greater than, I'm sorry, less than or equal to, up to 4 solutions. The only reason I say less than or equal to is, I don't know if you can think back, but at times when we were solving quadratics, sometimes there were 2 solutions, but they were the same solution. And so we considered it one. And that would be the concept here as well. Okay? So what does the fundamental theorem basically give us? 3 things. It tells us the number of roots, it tells us the max number of zeros, and it tells us the max number of solutions. All of that comes from the degree of the polynomial. So that's key. And if you keep that in your mind, then it's going to help you. That's why earlier when we were looking at quadratics, I said to you, hey, this is a second degree. You always have to expect 2 solutions. And expecting 2 solutions helps you to make sure that you're always getting both solutions. For example, you don't need to write this. Look up here in the top right. You know, again, if you had something very, very, very simplistic like x squared equals 4, and you say to yourself, oh, this is quadratic. I know that there are up to 2 solutions. Therefore, when you take the square root of both sides, hopefully you don't forget the plus minus because you're expecting 2 solutions, right? So again, the fundamental theorem helps us in those respects, as it just helps us to predict some things. Okay, what did I do? Who knows? I'm probably on the next page. All right, so let's continue on. So that brings us then to number 1, the conjugate root theorems. The conjugate root theorems. All right, we've talked about conjugates before. I'll refresh your memory in a second. So there's a couple conjugate root theorems. The first one is the irrational root theorem. All right, getting confusing. Hopefully when we think of an irrational number, hopefully we think of something like the square root of 3, the square root of 7, pi. Remember, irrational numbers are numbers that we cannot express as a fraction. Right? Irrational numbers. Square root of 3, square root of 5, pi, e, and some other things. So the irrational root theorem says if a plus, and let's stick in here, let's go the square root of b. Okay, so now we have an irrational root, a plus the square root of b. If that is a root of some function, p of x, then it's conjugate. And somebody tell me the conjugate of a plus the square root of b. You should all know if we're remembering. We've all learned it. What's the conjugate of a plus the square root of b? Whoa. Surely, nobody. Somebody's got to remember the conjugate. Nobody? We've used them like at least 2 times already. All right, for example, let me try to, here's one of the ways we used it. If we were doing division and we ended up with something like this, we said, oh, we can't have a radical in the denominator. We've got to multiply the bottom by the conjugate. And what would we have multiplied the bottom by? Are you telling me you don't remember that either? All right, time for me to give the speech again. I can teach the stuff to you. You have to study it to remember it. I'm just telling you. All right, because we've learned this. All right, we've learned what to. Nobody remembers the conjugate? Huh? Okay. All right. I'll show it to you and then I'll explain it in words. That's the conjugate. It's really simple. Conjugates. What was that back there? Say it, please. Huh? You knew it. Just didn't want to say it. Thanks. All right. So, hey, conjugates are just, they make up a difference of two squares. Remember, the middle sign is different. All right, that's scary if you guys don't remember conjugates. So, what's the conjugate? A minus the square root of B. Two conjugates together form a difference of two squares. So, here's what we're saying. If you have one root where it's an irrational root, it has an irrational number in it, which normally is going to be a square root of a number, then you know you also have its conjugate as a second root. Second root. That's the irrational root theorem. So here's a couple quick examples. If x minus the square root of 3 is a root, then we also know what's another root. X plus the square root of 3 is also a root. It has to be. All right, good. Now we have two roots instead of one. So 2 for the price of 1 sale. Buy one, get one free. And therefore, then if 2x plus the square root of 7 is a root, then obviously, what's the other one going to be? 2x minus the square root of 7. And it doesn't matter. The front term could even be negative if you wanted to. It doesn't matter. You just always change the sign in the middle. And again, these form a difference of two squares. So that is the conjugate root theorem. Let me go higher for you here. All right, so then there's also the complex root theorem. What kind of numbers are complex numbers? I already said at the beginning, imaginary, right? So this would be a plus bi. A plus bi. Now you got an imaginary number as part of your root. By the way, what's the value of I? What's the value of I? What's the value of I? Square root of -1. All right. Square roots of negative numbers are imaginary numbers. We also learned that already, but that's okay. All right, so the complex root theorem. So if a plus bi is a root, then it's, again, conjugate. And so what's the conjugate of a plus bi? A minus bi is also a root. So therefore then, example 1, if you had x plus 2i as a root, then we also know x minus 2i is a root. And if 2x minus I is a root, then 2x plus I must be a root. They're conjugates. They're conjugates. Okay, how do we use all this? We use all this in situations like this. So C, let's do this example. And I know there's not a ton of room here, so you're going to have to be kind of efficient in your use of your space in the amount that's left here. All right, so here's the situation. They want us to find all the zeros of this function, p of x equals 2x cubed minus x squared minus 4x plus 2. How many possible zeros are there? How many total possible zeros are there? 3. All right, that's how we started the whole thing, right? The fundamental theorem of algebra tells us how many possible roots or zeros. Okay, so we have up to 3. They also tell us this. They give us a piece of information. Actually, they're making the problem easier for us. They tell us that we already know that x plus the square root of 2 is a root. We already know that. They tell us it's a factor. Same thing. It's a root. Therefore, can you tell me another factor that we know if we know that x plus the square root of 2 is a factor? Exactly. So let's take these two. So if we know x plus the square root of 2 is a factor, we also know x minus the square root of 2 is a factor. So we know that these two roots are factors. And by the way, at this point, we could already name two of the zeros. Can anybody give me the name of two of the zeros? Again, it's going to be x equals. From this first left root, if you solved it setting it equal to 0, you would get x equal negative square root of 2. And if you solve the right one, you get x equal positive square root of 2. All right, we already have two of the three zeros, if indeed there are three. Right, it can be up to or equal to 3. How do we find that last 0? All right, so let me just pause for a second, try to refresh your memory on something else. If we had x, y, z equals 0, then we know either x equals 0, y equals 0, or z equals 0, or a combination thereof. It's the only way you're going to end up with 0. If you have factors that equal 0, the only way you can figure it out is you're going to determine at least one of them has to be 0. Okay, and that was the basis of solving quadratics by factoring, set it equal to 0, and factor. Polynomials the same way. We have to set it equal to 0, and we got to factor it. So, earth to sleepers, you may need to stand up if you're going to fall asleep, because that's not good to fall asleep. Okay, so let's suppose, let me see if I can come up with a good example here. Let me go easy, this way I don't have to worry about it. Let's suppose we had the number 50. All right, forgetting everything you know about simplistic numbers, if I told you 5 was a factor, how could you get another factor? Couldn't you divide the 50 by the 5? All right, and you would end up with 10, and you can then factor the 10. This is what we have to do here. So we have to factor. All right, let me get rid of all this stuff. Go. So we have to factor 2x cubed minus x squared minus 4x plus 2. That's what we're after, factoring it. In order to factor it, what do we divide into it? So here's where we're heading. You can write this 2x cubed minus x squared minus 4x plus 2. We've got to divide something into it. Now, honestly, if I only knew one factor, I would divide that factor into it. That's what we were doing last week to try to continue factoring things. We used the remainder theorem to try to find one factor, divided that factor into the polynomial, and then tried to continue factoring from there. However, because this one involves an irrational root, we have more than one factor, we have two. And it would be to our advantage to figure out what the two of them together equal. So what I want to do is I want to multiply this out. Multiply this out. And it's a difference of 2 squares, so it multiplies very, very easily. Front times front is x squared. Front times back is a negative square root of 2 times x. And then the positive square root of 2 times x is positive. So that's 0, right? Difference of 2 squares, they always add out. So again, what's the shortcut of multiplying difference of 2 squares? Front times front, back times back. X times x is x squared. Positive square root of 2 times negative the square root of 2 is a negative the square root of 4. And negative the square root of 4 is? Negative the square root of 4 is 2, and you end up with x squared minus 2. If you multiply all that out, you get x squared minus 2. So that's what we want to divide into our polynomial. And hopefully it'll divide in evenly. If it divides in evenly, there would have been 3 zeros. If it doesn't divide in evenly, there would only be 2 zeros, the ones we already have. But we don't know if there's 2 or 3, and we've got to do the division to find out. So we got to divide it in to figure it out. All right, long division. Front divided by front. 2x cubed divided by x squared is a 2x. I'm going to put it in the 2x column. All right, front x squared times the 2x is the 2x cubed. Negative 2 times the 2x is a negative 4x. Subtract. So that gives us a 3x. I'm sorry, this is, where am I at here? This is I am off. Hold on. That's why if you keep doing everything, hopefully you'll catch your mistake, and that's where I caught it. All right, so this is a 2x cubed. X squared times 2x is 2x cubed. We're good there, not a problem. But I had to be careful. If you notice, a negative 2 times the 2x is a negative 4x, and that's got to go over here, right? In the x column. I stuck it in the x squared column, doesn't belong there, and when I went to do my subtraction, I noticed, obviously, I made a mistake. Okay, the 2x cubes add out, and the negative 4x and the positive 4x add out. Good. That's all 0. What would you do next? Long division. Just say it. Bring down what you got. All right, so let's bring down then the negative x squared, and let's bring down the positive 2. And again, let's go front divided by front. Negative x squared divided by x squared is a negative 1. Negative 1 times x squared is a negative x squared. Negative 2 times a negative 1 is a positive 2. But remember, we're subtracting, and lo and behold, we get 0. Beautiful. There was indeed a third factor. And here's what we found. This times this times this equals our original polynomial. So just to be clear, here are the factors. The x plus the square root of 2, the x minus, the square root of 2, and the 2x minus 1 are the factors. Luke?
For the multiplication part, if there was a remainder, so would that mean there's just those two factors?
It would just be then the two conjugates were the only zeros for that one, yes. And are the only even factors. Okay, so remember, to get a 0, you would set each of these equal to 0, right? And solve the little equation. So on the conjugates, as we've already said, you get plus or minus the square root of 2. And then what's a 2x minus 1 when you solve it for x? It's a positive 1/2, right? And there are zeros. Plus or minus the square root of 2 are 2 of them, and the other one is a 1/2, right? And again, how do you finish off getting the 0? Set the little binomial equal to 0 and solve that little equation. Okay. All right, and way back here, I should have said set it equal to 0 and find the factors. Right? So that's one scenario. I'm trying to show you, here's the thing, there are more than one possible scenario. And you have to be aware of the differences, and you have to look at what you have and determine, okay, with what they give me, how do I proceed? And that's why you need to study. What in the world happened here? My whole page disappeared? Okay. Let me bring it up here.
You had it.
Yeah, I know I had it, but it's gone, so it doesn't matter. Okay, what are we in? Lesson 6 point what? 6.7. All right, so it's just page 2. Okay, so here's the second scenario. Write a polynomial function of least degree if 3/5 and -5 are zeros. Now we're going kind of backwards. In the first example, they asked you to find the zeros. In the second example, they give you the zeros and they want the polynomial. What polynomial produced these zeros? Okay. We have to work backwards, and sometimes for students that's a little difficult, so let me try my best to help make this, have it make sense for you. Okay? So we've got negative 2, 3/5, and negative 5i are zeros. And I didn't want that negative 2 to be there. Get rid of that negative 2. First edition notes. Is that there on your notes? Okay, get rid of that. Just 3/5 and negative 5i are zeros. Okay, let's start off with the 3/5. Where does 3/5 come from? Okay, whenever you want to find the 0 and work backwards, do an x minus and then the value they give you. So you have an x minus 3/5. If you set that equal to 0, wouldn't you get x equal 3/5 as a 0? Again, we're working backwards, and I know it's a little confusing. But here's one other thing we want. We don't like fractions over here. So to get rid of that fraction is the same concept of any situation getting rid of fractions. If I multiply this by a 5/1, I can also multiply that by a 5/1. I'm just going to get rid of that bottom 5 denominator. And we end up with the better form of 5x minus 3. The shortcut is just take the denominator and stick it over with the variable. That's the shortcut. If you do 5x minus 3 and set it equal to 0, don't you get 3/5? You do. And again, I know it's tricky because we're working backwards. That is where you end up. Okay, in the second set, it says negative 5i are zeros. So now we have a negative 5i. So again, if I were to set the template, it's x minus and then minus 5i, right? For an x plus 5i binomial. Again, if you solve that for 0, would you not get x equal negative 5i? You would. And again, to work backwards, you always start with the x minus and then whatever they give you as the 0. So x plus 5i. But because we just learned the complex root theorem, do we know another root? If x plus 5i is a root, what's another root? X minus 5i. So again, this came out of the complex root theorem. Okay? So here's where we're at. Here are our factors. We've got the 5x minus 3. We've got the x plus 5i, and we've got the x minus 5i. Now, the only way to polynomial is to multiply it all out. Because the right are conjugates and it's a difference of 2 squares, it's to my advantage to multiply these out first. I'm going to do it in red. So I'm going to do this part first. So x times x is x squared. Again, the middles, the outer and the inners add up to 0. So to finish off, positive 5i times negative 5i, and I better show this, is a negative 25i squared. Do you agree with that? Okay. So now we're at 5x. Look at that. Wow. Dyslexic. 5x minus 3 times an x squared. All right. Got to remember again. We weren't good at remembering our imaginaries earlier. Instead of writing negative 25i squared, what do we write? All right, I heard some plus 25s. All right, it's coming back to you. Good. I know it was last year, but it was only like a month ago. All right. So, and for those of you that forgot, an I squared is a -1, right? And a -25 times a -1 is a +25. Okay, now we got to finish multiplying out. I'm going to do it in black so it stands out. 5x times x squared, 5x squared. 5x times 25, what is that, 125x? Cubed. Thank you. 5x cubed plus 125x. -3 times an x squared is a -3x squared. And finally, a -3 times a +25 is a -75. And I'm going to clean up my final answer. Write a polynomial function of least degree. So I'll use f of x. So I'm going to write a function. And I'm going to put my powers in order. 5x cubed minus 3x squared plus 125x minus 75. That's tricky. But you have to work backwards. All right, so the situation here where they said, hey, these are the roots, these are the zeros, tell me what the original function was. Work backwards. Multiply it all out, voila, you're there. All right, alley roll here. And being there are no hands up, because there never are hands up in this class for some reason, although I know the reason. Number 3. All right, here's another solve. Solve a polynomial equation, or define the zeros implies set it equal to 0. Oh, Windows 10, you're driving me crazy. Set it equal to 0, then factor, right? So first example, would you agree we got to move the -6 to the other side? So now we're at x cubed minus 7x plus 6 equals 0. They didn't tell us that something's a factor of this one, did they? So how are we going to solve this and or find the zeros? It's kind of a similar question. Solving a quadratic equation and the zeros of a polynomial function is the same thing. Now we're back to last week. We have to find a factor. Thankfully, the front coefficient is a 1 and the back number is a 6. I'm going to list out my possible factors. Stop doing this screen. So again, I'm going here, I'll do them in green. Going off of the 6, I can have an x plus 6, an x plus 1, an x minus 6, an x minus 1, an x plus 2, an x plus 3, an x minus 2, and x minus 3. There are 8 possible factors with the 1 in front of the x cubed and the 6. Okay, so again, you got to do the remainder theorem, right, to figure out which one of the 6. All right, for time's sake, let's try x minus 1. So our first try is an x minus 1, which implies we're going to do f of 1. Good, you remember that. Very good. So wherever our variable is, we're going to put in 1 of the x cubed minus 7x plus 6. 1 cubed is 1. Oops, this is a 1, by the way, as well. 1 cubed is 1. -7 times 1 is -7. 1 minus 7 is a -6. -6 and 6 is 0. Woohoo! It worked. But then again, I'm trying to save some time. What's the next step? Once we have a factor, what's the next step? Long division. Okay, so just remember, there's that page now, huh? Just remember, in our first example, they gave us a 0. Man, this is all goofed up. I don't even know where I am anymore. In the first example, they gave us a 0. They gave us a factor. In fact, they gave us 2. And therefore, we were ready to go right into the multiplying. In this situation, we had to find the factor. And we found it. And now we're ready for long division. So now we're going to take that x minus 1, and we're going to divide it into the x cubed. I'm going to leave an x squared spot. I might need it. Minus 7x plus 6. Remember, this is what we're working off of. All right, long division. Front divided by front. X cubed divided by x is an x squared. Oh, yes, we needed that spot. And we've done long division before, so I'm not going to do the rest of it. But when you do it, you get x squared plus x minus 6. At this point, then, here's where we're at. X minus 1 times x squared plus x minus 6 equals our 0. So I'm going to let you catch up, and let me pause and try to make sure you're following. We took this, and we have now factored it into this, right? And now we're going to see if we can further factor the trinomial. 2 parentheses, right, trial and error on the trinomial. Factors of x squared are x and x. Can you get a negative 6 to produce a positive 1 in the middle? You can if you do a positive 3 and a negative 2, right? That gives you the outers and inners to add up to the positive x, and we know we have the right thing. Now remember, to solve or to find the zeros, you have to set each one of these equal to 0. And so we're going to get x equal 1 out of the front one. We're going to get x equal 2 out of the middle one. And we're going to get x equal negative 3 out of the last one. And there we are. And we found the zeros, or we solved the equation. If it's a function, we found the zeros. If it's an equation, we solved the equation. They're synonymous depending on whether you have an equation or a function. Equation or function. Third example. What if they give you something like this? Find the zeros. Okay, you should immediately say to yourself, to find the 0, Windows 10, to find the 0, I set it equal to 0, and I factor. And I'm looking at this x cubed minus 8, and I'm saying to myself, wait a minute. This is a difference of 2 cubes. We have a pattern to factor this thing. I don't have to go through that big, long process. We got a pattern. All right, hopefully you remember the pattern. Binomial, trinomial, right? Do the signs. The binomial sign always matches. The front is always opposite, and the back is always positive. Match, opposite, positive. The front of binomial is the cube root of the front. The front of the trinomial is the cube root squared of the front. The middle term begins with the cube root of the front. The back is the cube root of the back. The very back of the trinomial is that cube root number squared. 2 squared is a 4. And the middle is, again, that cube root. And I'm going to stick it in the front for a 2x. Okay, we're getting there. So we already know one of the zeros is x equals 2. That's from the front one. Uh-oh. Can we factor this trinomial? No, you can't. You can't factor an x squared plus 2x plus 4 and get factors. So therefore, I must use the quadratic equation. All right, so right here we're at x equal 2. And for here, I got to do x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Isn't math awesome? My time is going by very, very quickly. So negative b, the b is a 2, so that's negative 2 plus or minus the square root. B is again 2, 2 squared is 4. Minus 4 times 1 is a negative 4 times a 4 is a negative 16 all over 2a. Not go too high here. So hopefully you agree that's a negative 12. Oh, imaginary. Negative 2 plus or minus a negative 12 is a negative 4 times 3. Square root of negative 4 is a 2i. Still have the square root of 3 all over 2. Clean it up. Divide the 2 in to the 2's. X equal, I'll do this last part in red because here's our other roots. Negative 1. Negative 1 plus or minus I times the square root of 3. Found the 3 zeros. X equal 2 from the front binomial, and x equals negative 1 plus or minus I times the square root of 3 from the back. Man, I have 2 more examples. It's unbelievable. Oh, brother. I don't like that. All right, either way, there wasn't going to be homework tomorrow. There was going to be today, so I guess I'll have to flip it. All right, I'm going to stop. I'm not going to force it because I know things are complex here. We'll pick up here tomorrow.